Hey, there's our learning target. It says I can apply theorems about tangents. So let's get to it. Our first theorem that we're going to be looking at, and this is the first of 3 theorems we're going to look at in this video, first of 3, is called the tangent radius relationship. But let's review a little bit. If you recall, a tangent line is a line that intersects a circle in exactly one point. So there is a tangent line. Let's call this tangent line BC. Alright, so a tangent line is a line that intersects the circle in exactly one point. A radius is a line that connects the center of the circle and a point on the circle. So this is a radius OB. The center is point O, and so the radius OB connects the center to the point on the circle, point B. Okay, the tangent radius relationship says if a line is tangent to a circle, it is perpendicular to the radius drawn to the point of tangency. So what that implies is that line CB is perpendicular to line OB. That implies that the tangent is perpendicular to the radius at the point of tangency, which means this is 90 degrees. All right, let's do a problem that requires that we use this theorem. Here's our example 1, and we're going to have to use the theorem we just looked at. In the diagram below of triangle PAO, AP is tangent to circle O at point A. OB is equal to 5. So let's make that 5. BP is equal to 8, and the measure of angle OPA is equal to 23. What is the length of AP? What is the measure of angle POA? Well, before I go on any further, since this is a tangent line and this is a radius, and I know this is a radius because it's connecting the center and a point on a circle, I'm going to label this 90 degrees. Because that's the application of the tangent radius relationship. So I know that's 90 degrees. I'm being asked to find the length of AP here, so I'm going to label that X. Well, this is a right triangle, isn't it? And I know I need to use the Pythagorean theorem generally if I want to find the missing side of a right triangle, but I don't know what this side is here, or do I? Yeah, I actually do know the length of this side. Since OB is a radius and OA is a radius, they are both equal to each other. So OA is 5. So we got ourselves a nice right triangle here. You see it? And we're going to use the Pythagorean theorem to find X. But let's just go ahead and label this hypotenuse 13. So we're going to get x squared plus 5 squared equals 13 squared, right? This has to be C. This has to be the hypotenuse in your Pythagorean theorem. So we get x squared plus 25 equals 169. Minus 25 from both sides. We get x squared equals 144. We're going to square root both sides. So we get x equals 12. So that means AP is equal to 12. Now, to find the missing angle POA, so that's this angle here, I'm going to go ahead and label that Y. So to find angle Y, we know these 3 angles have to add up to 180. We know Y plus 90 plus 23 have to add up to 180. So we know that Y is equal to 67 degrees. Okay, so that's the application of the first theorem, the tangent radius relationship, right? So you need to know that a tangent is going to be perpendicular to the radius at the point of tangency. So the minute you see that, just put a 90-degree angle box there, and it will make things clearer for the rest of the problem. Here's our second theorem for the video, tangents drawn from an external point. And it basically says tangent segments to a circle from the same external point are congruent. So in this diagram, AB is congruent to AC. That means that this line is equal to this line. So if you got two tangent segments and they're drawn from the same external point, they are equal to each other. This is also known as the hat theorem. I'll show you why it's called the hat theorem. Because if you rotate this thing, let's go ahead and rotate that. I have to erase that. And that's equal to that. Looks like a hat, doesn't it? Looks like somebody here is wearing a hat. So the hat theorem says that these two tangents are equal to each other. All right, let's do two problems where we have to use this theorem. In the accompanying diagram, AB and AC are tangents to circle O. So we got two tangents drawn from the same point, so we know that automatically they have to be equal to each other. If the measure of angle ABC equals 72, so let's label this 72 degrees, what is the measure of angle A? So we're going to label that X. Well, we know that we are dealing with an isosceles triangle because AB is equal to AC by the tangents drawn from the same external point theorem. So let me just erase that to make some room. So we know these two lines are equal to each other, so this has to be an isosceles triangle. So that means that these two angles here are equal to each other. So this is also 72 degrees because it's isosceles. So X plus 72 plus 72 equals 180. So that's going to be X plus 144 equals 180, right? 70 is 114. Yep, 144 minus 144 from both sides. And we are going to get X equals 36. So that means angle A is equal to 36 degrees. Let's try another one where we got to use the hat theorem. Now this one doesn't look like the hat theorem right away, but you'll see that it is the hat theorem in a second. It says in the diagram below, triangle ABC is circumscribed about circle O, and the sides of triangle ABC are tangent to the circle at points D, E, and F. If AB equals 20, AE equals 12, and CF equals 15, what's the length of AC? So because of the hat theorem, I know that this line is equal to this line, right? These two lines are equal to each other. I also know this line is equal to this line. And finally, I know that these two are also equal to each other, right? That's our hat theorem there. I know that AB is equal to 20, so I'm going to write 20 there for that. And it says AE equals 12. So if AE equals 12, I know that AD also equals 12. And it says CF equals 15, so let's write 15 here. And that means that DC is also 15. And now it says, what is the length of AC? Well, to get AC, all we have to do is just add the 12 and the 15. And 12 plus 15 is equal to 27. Choice 4 is the answer. So, right, we were told AB is 20. We were told that AE is 12, so this is 12. This has to be 12. Tangents from the same external point. We were told CF is 15, so if that's 15, this is 15. They want AC, just add these two segments that make up AC. Okay, one last theorem, the common tangents theorem. So common tangents are lines or segments that are tangent to more than one circle at the same time. And it might just help if we just do a problem and then talk about the theorem. So let's do example 4 and then we'll talk about the theorem. It says how many common tangent lines can be drawn to the circles shown below. So they want to know, right, how many common tangent lines can you draw for these two circles. So a common tangent is, it says lines or segments that are tangent to more than one circle at the same time. So let me draw a common tangent. Got to fix that one up here because it's a secant right now. So there's one common tangent. So how many of these bad boys can I draw? How many common tangents can I draw when two circles are separated like this? Well, there's one. I know I can draw another one like this. So that's 2 common tangents so far. I know that I can draw another one going this way. So that's 3. And there's one more that I can draw. That's 4. So I can draw a total of 4 common tangents here. And here's just a summary of how many common tangents you can draw for different scenarios. So if the circles are separated, you could draw 4 common tangents. If the circles are tangent to each other, you can draw 3 common tangents. Right? The circles are tangent to each other. If the circles are overlapping, you can draw 2 common tangents. If the circles are tangent to each other but internally, meaning one circle is inside the other one, you can only draw 1 common tangent. And if the circles are concentric, meaning one is inside the other one but not tangent to each other, or they have the same center, you can't draw any common tangents. And same for this case here. Okay, let's do a quick summary. So we looked at three theorems. The tangent radius relationship, which says that the tangent is perpendicular to the radius at the point of tangency. The second one was tangents drawn from the same external point. That was our hat theorem. And the last one was common tangents. So I hope this video helps with tangents. Have a good one.